welcome to this problem walkthrough. Today, we'll be exploring problem number 694, number of distinct islands. This is an exciting and engaging question that focuses on grid traversal and shape identification. We'll dive into the problem, examine different approaches, and break it down step by step. Let's get started. In this problem, you are given a binary matrix called grid, where each cell is either 0 or 1. Here, 0 represents water, and 1 represents land. An island is defined as a group of ones that are connected either horizontally or vertically, meaning they are four-directionally connected. You can assume that the edges of the grid are always surrounded by water. Now, the task is to find the number of distinct islands in the grid. Two islands are considered distinct if their shapes are not identical when you translate or shift one to match the other. For example, consider two islands represented in the given diagrams. Although they are positioned differently in the grid, their shapes are identical when translated, so they are not considered distinct. Your goal is to return the total number of islands that have unique shapes. The input to the problem is an integer matrix grid of size mxn. Each cell in the matrix will either contain a 0, representing water, or a 1, representing land. The output is a single integer, which represents the total number of distinct islands in the input grid. Let's look at an example to understand this better. Consider the grid provided in example 1. Here, the grid has two islands, but both share the exact same shape. As a result, even though there are two islands visually, they count as only one distinct island because their shapes match. Here's a detailed explanation for example 1. In the grid, the first island, located in the top left corner, has the following shape when isolated, a 2x2 block of land. Similarly, the second island, located in the bottom right corner, also forms the exact same 2x2 shape. When we translate or shift one island to overlay with the other, their shapes align perfectly. Since they are identical in shape, they are not considered distinct. This is why the output for this example is 1, as there is only one distinct island shape. Now, consider example 2, where the grid contains multiple islands with different shapes. The output for this example is 3 because there are 3 unique island shapes. Let's break this down. The top left island has an L-like shape, the top right island forms a simple horizontal line, and the bottom right island creates an inverted L-like shape. Each of these shapes is unique, meaning no two islands can be translated to match one another. As a result, the grid contains 3 distinct islands, and the output is 3. In example 3, the grid contains 2 islands, and both have distinct shapes. The first island, located in the top left corner, forms an L-like shape with 3 blocks in a row and one extending downward. The second island is in the bottom right corner and has a different shape, resembling a rotated and shifted L. Since these two islands have unique shapes that cannot be translated to match each other, the output is 2. This highlights the importance of focusing on the shape of each island rather than its position in the grid. The second example from this grid, the bottom right island, forms a rotated L shape. Together with the earlier top left L-shaped island, we confirm that there are 2 distinct island shapes in total. Now, let's consider the constraints for this problem. The dimensions of the grid, m and n, can range from 1 to 50. Each cell in the grid will be either 0 or 1, representing water or land, respectively. Additionally, the total number of land cells in the grid will not exceed 200. These constraints ensure the problem is computationally feasible with the provided input sizes. Finally, let's think about some edge cases to validate your solution. For the smallest possible grid, such as grid equals 1 or grid equals 0, the outputs will be 1 and 0, respectively, since there's either one small island or no land at all. For a grid with no land, like grid equals 0, 0, 0, 0, the output is 0 because there are no islands. In contrast, for an all-land grid, like grid equals 1, 1, 1, 1, the entire grid forms one large island, so the output is 1. Lastly, for grids with complex shapes, it's important to ensure that only translations are considered, and other transformations like rotations or reflections are ignored. This ensures the distinctness of islands is based purely on their translatable shapes. To solve the problem of counting distinct islands, we first considered a brute force approach. The idea here is to traverse the grid, identify each island using a depth-first search or breadth-first search, and then record the shape of the island by noting the relative positions of its cells with respect to a reference point, such as the top left corner of the island. Once we have the shapes of all islands, we can use a set to store these shapes and count how many unique ones exist. The intuition behind this is that the structure of an island is determined by the layout of its cells relative to its starting point, and by normalizing these coordinates, we can compare islands effectively. This method has a time complexity of O(m*(n), because each cell in the grid is visited once. However, the space complexity depends on the size of the islands and the number of unique shapes stored in the set, which can become memory intensive for larger grids or grids with many islands. While this approach works, it is less efficient in terms of memory usage and could be improved upon. To address the inefficiencies of the brute force approach, we look at an optimized strategy involving canonical shape representation. Instead of storing all the relative positions of an island's cells, we encode the island's shape based on the traversal path itself. For example, as we traverse the island, we record directions like up, down, left, or right to generate a unique string representation for the island. This ensures that identical islands, regardless of their position in the grid, will produce the same traversal path string. By storing these encoded strings in a set, we can count distinct island shapes more efficiently. The key insight here is that the traversal path uniquely identifies the shape of an island without needing to store individual coordinates. This approach maintains the same time complexity, O(m*(n), since each cell is visited only once, but it reduces memory usage compared to the brute force method. However, it does require careful implementation to ensure consistency in how the traversal path is encoded, which can add some complexity to the solution. The core insight for this problem lies in recognizing that an island's shape can be uniquely represented by its traversal path rather than by storing absolute or relative coordinates. This realization simplifies the problem significantly, reducing the space complexity while also making it easier to compare island shapes. The optimized approach using canonical shape representation is chosen because it minimizes memory overhead by avoiding the storage of detailed relative coordinates. Instead, traversal paths are compact and straightforward to compare. Additionally, this approach is computationally efficient, making it well-suited for larger grids, and it provides a clear method for determining uniqueness. While the brute force approach is easier to implement and debug, it is less efficient in terms of memory usage. On the other hand, the optimized approach requires more careful implementation but is far more scalable and robust. The final strategy involves using depth-first search to traverse the grid and encode each island's shape as a traversal path string. These strings are stored in a set, and the size of the set ultimately gives us the count of distinct islands. This method strikes the right balance between efficiency, scalability, and clarity, making it the ideal solution. To solve the problem of finding the number of distinct islands in a 2D grid, we first need to break it down into clear steps. The grid is a 2D array where 1 represents land and 0 represents water. The goal is to identify unique island shapes, where an island is a group of connected 1s, and 2 shapes are considered identical if one can be transformed into the other by rotation or reflection. We begin by parsing the grid, which involves iterating over every cell to ensure we identify all potential islands. When we encounter A1, it marks the start of an island, and we initiate a depth-first search, or DFS, to explore all connected cells. The DFS is particularly effective here because it systematically visits all land cells in an island while marking them as visited, such as by setting their value to 0, to prevent revisits. As we traverse the island, we record the relative positions of each land cell with respect to the starting point, which helps us define the island's shape in a way that's independent of its location on the grid. When recording the shape of an island, relative positions are crucial because they normalize the shape to its starting point. For example, if the starting cell is x0, y0, and another cell is x, y, we record the relative position as x0, y, y0. This ensures the shape is the same no matter where the island appears in the grid. Once we have the shape, we need to account for all possible rotations and reflections, which gives us up to 8 transformations of the shape. These include the original orientation, rotations by 90, 180, and 270 degrees, and their reflections. Among these transformations, we select the lexicographically smallest one to represent the shape's canonical form. This guarantees that identical shapes, even if rotated or reflected, are treated the same. To keep track of unique shapes, we store these canonical forms in a set. Using a set is efficient because it automatically handles duplicates, ensuring that only distinct shapes are counted. Finally, the size of the set gives us the total number of unique island shapes in the grid. Understanding the key insights of this approach is essential. First, relative positioning ensures that the shape representation is independent of the island's location in the grid. Second, by normalizing shapes, we account for rotations and reflections, reducing the problem to finding unique canonical forms. Finally, using a set to store these canonical forms simplifies the task of identifying unique shapes, as it inherently avoids duplicates. The main data structures we use include the grid itself, which is modified during the DFS to mark visited cells, a set to store the canonical forms of shapes, and a list to temporarily hold the relative positions of an island during the DFS. The pseudocode outlines the approach. We define a number distinct islands function that takes the grid as input. Inside, a helper DFS function explores the grid, marking cells as visited by setting them to 0 and recording their relative positions. After traversing an island, the shape is normalized, and the canonical form is added to the set of unique shapes. Finally, the length of the set is returned as the result. The normalization process is key to ensuring that all equivalent shapes are treated as the same. To normalize, we generate all 8 transformations of the shape, including the original orientation, its rotations, and reflections. For each transformation, we sort the coordinates to standardize their order, and then we select the lexicographically smallest transformation to represent the shape's canonical form. This guarantees that no matter how the shape is oriented in the grid, its representation is consistent. In the implementation, we iterate through every cell in the grid. When a land cell is found, a DFS is performed to determine the shape of the island. The shape is then normalized using the normalize function, and the resulting canonical form is added to the set of unique shapes. The use of a set ensures that only distinct shapes are retained. Once all cells in the grid have been processed, the function returns the size of the set, which represents the total number of unique island shapes. Now let's analyze the complexity of the algorithm. For time complexity, the DFS visits each cell once, so traversing the grid takes m*n, where m and n are the dimensions of the grid. Normalization involves sorting and generating transformations, which takes k*log k, where k is the size of the island. In the worst case, k could be the total number of cells, or m*n, making the overall time complexity m*n. For space complexity, the DFS call stack requires k space, where k is the size of the island, and the list that stores the shape also uses k space. Additionally, the set for unique shapes requires u*k, where u is the number of unique islands. Finally, we need to handle edge cases, such as an empty grid or a grid with only water, where the result should be 0. Single-cell islands must be handled properly, and the algorithm must be efficient even for large grids with dense islands. This ensures robustness and scalability in various scenarios. This Python solution efficiently calculates the number of distinct islands in a given 2D grid. The problem involves identifying unique island shapes by exploring all connected land cells, represented as ones, in a 4-directional manner. The uniqueness of an island's shape is determined by its traversal path. The implementation begins by initializing helper variables, rows and calls to store grid dimensions, visited to track already visited cells, and unique underscore shapes to store unique island shapes. The DFS function is defined to perform depth-first search for exploring connected land cells starting from a specific cell. Inside the DFS function, a shape list is appended with a direction marker to record the traversal path. Movement is made in all 4 possible directions, down, up, right, left, while ensuring the next cell is within grid boundaries, unvisited, and contains land, 1. For each move, the DFS recursively continues exploration. A special backtrack marker, B, is appended to shape when backtracking occurs, ensuring the traversal path captures the complete structure of the island. The main loop iterates through each grid cell. Upon encountering an unvisited land cell, it initializes a new shape list and performs a DFS starting from that cell. The resulting shape is converted to a tuple, immutable, and added to the unique underscore shape set, ensuring only unique island shapes are stored. Finally, the function returns the size of the unique underscore shape set, representing the number of distinct islands. This solution is efficient due to its use of DFS for traversal and the set data structure for storing unique shapes. It handles edge cases, such as grids with no islands or entirely filled with land, correctly. The algorithm operates in O, rows asterisk calls, time complexity, as each cell is visited once. Here, we start by defining a method called numberDistinctIslands, which takes a 2D grid as input. This grid represents the map where each cell is either land, represented by 1, or water, represented by 0. First, we calculate the number of rows and columns in the grid. Then, we initialize a hash set called uniqueShapes, which will store all the distinct island shapes we encounter. We also create a 2D Boolean array called visited to keep track of the cells we've already processed during our depth-first search. Next, we iterate through each cell in the grid using a nested loop. If we encounter a land cell, represented by 1, that has not been visited yet, we initiate a depth-first search from that cell. To describe the shape of the island, we use a string builder called shape and pass it along with the current position and an initial direction of O, which stands for origin. After the DFS completes, the shape of the island is added as a string to the uniqueShapes set. Once we finish traversing all cells, the size of the uniqueShapes set gives us the number of distinct island shapes, which we return as the result. The DFS method is designed to explore each island and encode its shape. We start by marking the current cell as visited and appending the direction of movement to the shape string. This helps us uniquely represent the island's shape relative to its starting point. The directions array defines the possible movements, down, up, right, and left, represented by D, U, R, and L, respectively. For each direction, we calculate the new row and column indices. If the new cell is within the grid bounds, is unvisited, and is part of the land, we recursively call DFS on the new cell. This process ensures that the entire island is explored, and its structure is encoded based on the sequence of movements. By the end of this traversal, the shape string holds a unique representation of the island, which is critical for identifying distinct island shapes. In this first example, we have a simple 3x3 grid with 2 distinct islands. The algorithm starts by initializing the number of rows and columns, a set to track visited cells, and another set to store unique island shapes. As we iterate through the grid, we encounter the first unvisited land cell at 0, 0. This triggers a depth-first search, or DFS, where we explore all connected land cells and record the relative shape of the island. Starting at 0, 0, we mark it as visited and begin constructing the shape with the origin marker O. From there, we move downward to 1, 0, adding D to the shape. Moving right to 1, 1 is invalid because it is water, and moving left to 0, 1 is out of grid bounds. Backtracking to the previous cell adds B to the shape. From 0, 0, we next move right to 0, 1, adding R to the shape. Finally, we backtrack once more to 0, 0, completing the shape as O, D, B, R, B. The completed shape, represented as the tuple O, D, B, R, B, is added to the set of unique island shapes. The iteration continues, skipping over all previously visited cells, until we reach the second unvisited land cell at 2, 2. Starting a new DFS from this cell, we mark it as visited and initialize the shape with O. Since no valid moves are available from 2, 2, we backtrack immediately, completing the shape as O, B. This shape, represented as the tuple O, B, is also added to the unique underscore shape set. At the end of the traversal, the unique underscore shape set contains 2 distinct shapes, O, D, B, R, B, and O, B. The algorithm returns the size of this set, which is 2. Now, we consider a different grid, where islands may appear rotated or flipped. In this second example, we have another 3x3 grid, but this time, the island is larger and shaped differently. As before, the algorithm initializes the required variables and begins iterating through the grid. At the first unvisited land cell, 0, 0, we start a DFS to explore the connected island. Marking 0, 0 as visited, we initialize the shape with O. Moving downward to 1, 0, we add D to the shape. From there, we move right to 1, 1, adding R, and then move further down to 2, 1, adding another D. After reaching 2, 1, all other potential moves are invalid or lead to previously visited cells, so we backtrack fully, adding multiple B markers to indicate the return path. The final shape becomes O, D, R, D, B, 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 which is added to the unique underscore shapes set. Since no new unvisited land cells remain, the algorithm identifies only one unique island shape in this example and returns one. In the final example, we have a grid with no land at all, every cell contains water. The algorithm initializes the grid dimensions, visited set, and unique underscore shapes set as usual. Iterating through the grid, every cell is found to have a value of 0, so no DFS is initiated. As a result, the unique underscore shapes set remains empty. The algorithm concludes by returning the size of this set, which is 0. To summarize, the DFS algorithm systematically explores each island, recording its shape using directional and backtracking markers. By storing these shapes as tuples in the unique underscore shapes set, we ensure that only distinct island configurations are counted, regardless of their position in the grid. This approach operates efficiently with a time complexity of O, rows asterisk calls, as each cell is visited exactly once. The outputs for the three examples are 2, 1, and 0, respectively. To analyze the time complexity of the solution, we start with the outer loop. The algorithm iterates over every cell in the grid using two nested loops, which results in an O, rows asterisk calls, traversal, where rows and calls represent the grid's dimensions. Now, for each land cell that hasn't been visited, a depth-first search, DFS, is triggered. In the worst-case scenario, the DFS could theoretically visit all cells in the grid. However, since each cell is visited only once, the total DFS work across the entire grid is also bounded by O, rows asterisk calls. Additionally, during the DFS, the algorithm encodes the shape of the island by recording the path taken, including backtracking. The size of this shape list is proportional to the number of cells in the island. Across all islands, this cost is limited by the maximum number of land cells, which is at most rows asterisk calls. This ensures that all operations within the DFS remain efficient and scalable. Next, we consider the set operations used to track unique island shapes. The unique underscore shapes set is responsible for storing the encoded shapes as tuples. Each insertion or lookup operation in the set is, on average, O1. In the worst-case scenario, there could be as many as rows asterisk calls distinct island shapes, which means all set operations combined contribute an O, rows asterisk calls, cost. When we combine all these steps, the outer loop traversal, DFS calls, shape encoding, and set operations, the overall time complexity simplifies to O, rows asterisk calls. Now, turning to space complexity, the solution uses a visited set to ensure each cell is processed only once. In the worst case, this set could store all land cells, resulting in O, rows asterisk calls, space usage. Additionally, during the DFS for a single island, the shape list is used to store the encoded path of the island. The size of this list is proportional to the number of cells in the island, which is at most rows asterisk calls in the worst case. Another contributor to space usage is the unique underscore shape set, which stores the shape of each distinct island. In the worst case, there could be rows asterisk calls distinct shapes, and each shape could represent up to rows asterisk calls cells. This means the space required for the unique underscore shape set is also bounded by O, rows asterisk calls. Lastly, the DFS recursion stack contributes to the space complexity. The depth of the recursion stack corresponds to the size of the largest connected component, or island, which is at most rows asterisk calls. Combining all these factors, the overall space complexity of the solution is also O, rows asterisk calls. Now, let's compare this optimized approach with a potential brute force solution. A naive method might involve identifying and comparing islands by iterating over the grid multiple times. This would lead to a much higher time complexity of at least O, rows asterisk calls, caret 2, due to redundant comparisons and repeated processing of the same cells. In contrast, the optimized solution avoids such inefficiencies. It traverses each island exactly once using DFS, efficiently encodes its shape, and uses a set to verify uniqueness. This brings the time complexity down to O, rows asterisk calls. In terms of specific cases, the best case occurs when the grid contains only water, where no DFS calls are necessary, so the complexity remains O, rows asterisk calls. In the average case, with a mix of land and water cells, the complexity is still bounded by O, rows asterisk calls. Finally, in the worst case, where the entire grid consists of land, the traversal, shape encoding, and storage still scale linearly with the grid size, maintaining the O, rows asterisk calls, time complexity. To provide a more mathematical justification for the O, rows asterisk calls, complexity, we note that each cell in the grid is visited exactly once during the DFS. Key operations such as marking a cell as visited, encoding the shape, and inserting shapes into the set are all O1 per cell. The outer loops ensure that every cell is processed, which leads to the overall time complexity of O, rows asterisk calls. On the space side, the main contributors are the visited set, the shape encoding, and the recursion stack, all of which scale linearly with the grid size. This means the space complexity is also firmly O, rows asterisk calls. Together, this analysis confirms that the solution is both time and space efficient, scaling gracefully with the size of the input grid. When solving the number of distinct islands problem, there are a few common mistakes to watch out for. First, not handling edge cases can lead to incorrect solutions. For example, if the grid is empty or contains just a single cell, whether it's land or water, your solution might fail if these scenarios aren't accounted for. Always ensure you test for these edge cases. Another frequent issue is modifying the grid directly during traversal without making a copy. If you need the grid for other calculations after processing, marking cells as visited directly can disrupt those calculations and lead to unexpected behavior. Instead, consider using a separate visited matrix or restoring the grid to its original state afterward. Additionally, using an inefficient traversal method can create problems, especially on large grids. Recursive DFS, for example, may result in a stack overflow for large inputs. In such cases, iterative DFS or BFS is a better choice. Finally, overlooking or misimplementing the four cardinal directions up, down, left, and right can cause incomplete exploration of islands, so double-check your direction vectors carefully to ensure no cells are skipped. Another mistake to avoid is miscalculating time complexity. While it might be tempting to assume the algorithm runs in O, N, the actual complexity is O, N asterisk M, for a grid with N rows and M columns. It's critical to analyze both dimensions to provide an accurate complexity assessment. Now, in an interview setting, there are additional insights that can help you stand out. Start by clarifying assumptions early. Ask whether diagonal connections count as part of an island, as this can significantly affect your implementation. For large grids, scalability is key, so discuss strategies like iterative DFS, BFS with queues, or even union find to handle 10,000 by 10,000 grids efficiently. It's also important to address spacetime trade-offs. For instance, BFS requires extra memory for its queue, while iterative DFS minimizes stack usage but may be harder to code. Lastly, demonstrate pattern recognition by relating this problem to other graph traversal problems, such as counting connected components in a graph, to showcase your broader understanding. This problem is closely related to several other LeetCode problems, so practicing them can deepen your understanding. For instance, problem 200, number of islands, involves counting the number of islands in a 2D grid and is a foundational problem in this domain. Problem 695, max area of island, focuses on finding the largest island by area, which requires a similar traversal approach. Problem 463, island perimeter, asks you to calculate the perimeter of an island in a grid, which builds on the concepts you've already learned. Finally, problem 547, number of provinces, takes the idea of connected components into an adjacency matrix, showing how these techniques apply beyond grids. As for the techniques themselves, recursive DFS is a simple and intuitive choice, but it carries the risk of stack overflow on large grids. Iterative DFS, which uses an explicit stack, avoids this issue but can be a bit more complex to implement. Both approaches have their strengths and weaknesses depending on the problem constraints. BFS is another powerful approach, particularly useful for processing level by level or when dealing with large grid sizes. However, it does require additional memory for the queue, so that's a trade-off to consider. The union find algorithm, or disjoint set, is also worth discussing. It's highly efficient for dynamic grid processing, such as when land cells are added or removed during the problem. That said, it's more complex to implement and analyze, so it's best suited for specific variations of the problem. Finally, the flood-fill algorithm is an intuitive way to mark connected regions, and its trade-offs are similar to those of DFS and BFS. The choice of algorithm ultimately depends on the problem's constraints and what is being optimized, whether that's runtime, memory, or implementation simplicity. By understanding these alternative approaches and their trade-offs, you'll be well prepared to tackle this problem and its variations effectively. Great job working through this problem. We covered key concepts like grid traversal, shape hashing, and the use of DFS to solve the number of distinct islands problem. Keep practicing and applying these techniques to similar challenges. If you enjoyed this video, don't forget to like, share, and subscribe. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!